Databases and streams. We have drawn some comparisons between message brokers and databases. Even though they have traditionally been considered separate categories of tools, we saw that log-based message brokers have been successful in taking ideas from databases and applying them to messaging. We can also go in reverse. Take ideas from messaging and streams and apply them to databases. We said previously that an event is a record of something that happened at some point in time. The thing that happened may be a user action, for example typing a search query, or a sensor reading, but it may also be a write to a database. The fact that something was written to a database is an event that can be captured, stored, and processed. This observation suggests that the connection between databases and streams runs deeper than just the physical storage of logs on disk. It is quite fundamental. In fact, our replication log C implementation of replication logs on page 158 is a stream of database write events produced by the leader as it processes transactions. The followers apply that stream of writes to their own copy of the database and thus end up with an accurate copy of the same data. The events in the replication log describe the data changes that occurred. We also came across the state machine replication principle in total order broadcast on page 348, which states, if every event represents a write to the database, and every replica processes the same events in the same order, then the replicas will all end up in the same final state. Processing an event is assumed to be a deterministic operation. It's just another case of event streams. In this section we will first look at a problem that arises in heterogeneous data systems, and then explore how we can solve it by bringing ideas from event streams to databases. Keeping systems in sync. As we have seen throughout this book, there is no single system that can satisfy all data storage, querying, and processing needs. In practice, most non-trivial applications need to combine several different technologies in order to satisfy their requirements. For example, using an OLTP database to serve user requests, a cache to speed up common requests, a full-text index to handle search queries, and a data warehouse for analytics. Each of these has its own copy of the data, stored in its own representation that is optimized for its own purposes. As the same or related data appears in several different places, they need to be kept in sync with one another. If an item is updated in the database, it also needs to be updated in the cache, search indexes, and data warehouse. With data warehouses, this synchronization is usually performed by ETL processes. See data warehousing on page 91. Often by taking a full copy of a database, transforming it, and bulk loading it into the data warehouse, in other words, a batch process. Similarly, we saw in the output of batch workflows on page 411 how search indexes, recommendation systems, and other derived data systems might be created using batch processes. If periodic full database dumps are too slow, an alternative that is sometimes used is dual writes, in which the application code explicitly writes to each of the systems when data changes. For example, first writing to the database, then updating the search index, then invalidating the cache entries, or even performing those writes concurrently. However, dual writes have some serious problems, one of which is a race condition illustrated in figure 11-4. In this example, two clients concurrently want to update an item X. Client 1 wants to set the value to A, and Client 2 wants to set it to B. Both clients first write the new value to the database, then write it to the search index. Due to unlucky timing, the requests are interleaved. The database first sees the write from Client 1 setting the value to A, then the write from Client 2 setting the value to B, so the final value in the database is B. The search index first sees the write from Client 2, then Client 1, so the final value in the search index is A. The two systems are now permanently inconsistent with each other, even though no error occurred. Figure 11-4. In the database, X is first set to A and then to B, while at the search index the writes arrive in the opposite order. Unless you have some additional concurrency detection mechanism, such as the version vectors we discussed in detecting concurrent writes on page 184, you will not even notice that concurrent writes occurred. One value will simply silently overwrite another value. Another problem with dual writes is that one of the writes may fail while the other succeeds. This is a fault tolerance problem rather than a concurrency problem, but it also has the effect of the two systems becoming inconsistent with each other. Ensuring that they either both succeed or both fail is a case of the atomic commit problem, which is expensive to solve. See atomic commit and two-phase commit to PC on page 354. If you only have one replicated database with a single leader, then that leader determines the order of writes, so the state machine replication approach works among replicas of the database. However, In Figure 11-4 there isn't a single leader. The database may have a leader and the search index may have a leader, but neither follows the other, and so conflicts can occur. See multi-leader replication on page 168. The situation would be better if there really was only one leader, for example, the database, and if we could make the search index a follower of the database. But is this possible in practice? Change data capture. The problem with most databases' replication logs is that they have long been considered to be an internal implementation detail of the database, not a public API. Clients are supposed to query the database through its data model and query language, not parse the replication logs and try to extract data from them. For decades, many databases simply did not have a documented way of getting the log of changes written to them. For this reason, it was difficult to take all the changes made in a database and replicate them to a different storage technology such as a search index, cache, or data warehouse. More recently, there has been growing interest in change data capture (CDC), which is the process of observing all data changes written to a database and extracting them in a form in which they can be replicated to other systems. CDC is especially interesting if changes are made available as a stream, immediately as they are written. For example, you can capture the changes in a database and continually apply the same changes to a search index. If the log of changes is applied in the same order, you can expect the data in the search index to match the data in the database. The search index and any other derived data systems are just consumers of the change stream, as illustrated in Figure 11-5. Figure 11-5, taking data in the order it was written to one database, and applying the changes to other systems in the same order. Implementing change data capture we can call the log consumers derived data systems, as discussed in the introduction to Part Roman 3. The data stored in the search index and the data warehouse is just another view onto the data in the system of record. Change data capture is a mechanism for ensuring that all changes made to the system of record are also reflected in the derived data systems so that the derived systems have an accurate copy of the data. Essentially, change data capture makes one database the leader, the one from which the changes are captured, and turns the others into followers. A log-based message broker is well suited for transporting the change events from the source database, since it preserves the ordering of messages, avoiding the reordering issue of Figure 11-2. Database triggers can be used to implement change data capture. See trigger-based replication on page 161 by registering triggers that observe all changes to data tables and add corresponding entries to a changelog table. However, they tend to be fragile and have significant performance overheads. Parsing the replication log can be a more robust approach, although it also comes with challenges, such as handling schema changes. LinkedIn's database, Facebook's wormhole, and Yahoo's Sherpa use this idea at large scale. Bottled Water implements CDC for PostgreSQL using an API that decodes the write-ahead log. Maxwell and Debezium do something similar for MySQL by parsing the bin log. MongoRiver reads the MongoDB uplog, and Golden Gate provides similar facilities for Oracle. Like message brokers, change data capture is usually asynchronous. The system of record database does not wait for the change to be applied to consumers before committing it. This design has the operational advantage that adding a slow consumer does not affect the system of record too much, but it has the downside that all the issues of replication lag apply. See problems with replication lag on page 161. If you have the log of all changes that were ever made to a database, you can reconstruct the entire state of the database by replaying the log. However, in many cases, keeping all changes forever would require too much disk space, and replaying it would take too long, so the log needs to be truncated. Building a new full-text index, for example, requires a full copy of the entire database. It is not sufficient to only apply a log of recent changes, since it would be missing items that were not recently updated. Thus, if you don't have the entire log history, you need to start with a consistent snapshot, as previously discussed in setting up new followers on page 155. The snapshot of the database must correspond to a known position or offset in the change log, so that you know at which point to start applying changes after the snapshot has been processed. Some CDC tools integrate this snapshot facility, while others leave it as a manual operation. If you can only keep a limited amount of log history, you need to go through the snapshot process every time you want to add a new derived data system. However, log compaction provides a good alternative. We discussed log compaction previously in hash indexes on page 72, in the context of log structured storage engine. See Figure 3-2 for an example. The principle is simple. The storage engine periodically looks for logged records with the same key, throws away any duplicates, and keeps only the most recent update for each key. This compaction and merging process runs in the background. In a log-structured storage engine, an update with a special null value, a tombstone, indicates that a key was deleted and causes it to be removed during log compaction. But as long as a key is not overwritten or deleted, it stays in the log forever. The disk space required for such a compacted log depends only on the current contents of the database, not the number of writes that have ever occurred in the database. If the same key is frequently overwritten, previous values will eventually be garbage collected, and only the latest value will be retained. The same idea works in the context of log-based message brokers and change data capture. If the CDC system is set up such that every change has a primary key, and every update for a key replaces the previous value for that key, then it's sufficient to keep just the most recent write for a particular key. Now, whenever you want to rebuild a derived data system such as a search index, you can start a new consumer from offset 0 of the log compacted topic, and sequentially scan over all messages in the log. The log is guaranteed to contain the most recent value for every key in the database and maybe some older values. In other words, you can use it to obtain a full copy of the database contents without having to take another snapshot of the CDC source database. This log compaction feature is supported by Apache Kafka. As we shall see later in this chapter, it allows the message broker to be used for durable storage, not just for transient messaging. Increasingly, databases are beginning to support change streams as a first-class interface, rather than the typical retrofitted and reverse-engineered CDC efforts. For example, RethinkDB allows queries to subscribe to notifications when the results of a query change. Firebase and CouchDB provide data synchronization based on a change feed that is also made available to applications, and Meteor uses the MongoDB uplog to subscribe to data changes and update the user interface. VaultDB allows transactions to continuously export data from a database in the form of a stream. The database represents an output stream in the relational data model as a table into which transactions can insert tuples, but which cannot be queried. The stream then consists of a log of tuples that committed transactions have written to the special table, in the order they were committed. External consumers can asynchronously consume this log and use it to update derived data systems. Kafka Connect is an effort to integrate change data capture tools for a wide range of database systems with Kafka. Once the stream of change events is in Kafka, it can be used to update derived data systems such as search indexes, and also feed into stream processing systems as discussed later in this chapter.